a lesson on speeding up a chemical reaction. The basis behind speeding up the chemical reaction is based on something called the collision theory. The collision theory states simply that for a reaction to occur, the particles must collide in a successful collision. So reactions occur if particles hit or collide with each other in what is called a successful collision. Not all collisions are successful. They have to hit just right with enough energy to break and reform bonds. Sometimes they just bounce off. Sometimes, like it's a near miss, and they just glance off each other. So they got to hit straight on in the right place with enough energy for it to go. So the factors of what is a successful collision or not, the factors of a successful collision is the number of collisions, obviously the more collisions you have, the more chance you are to have a successful collisions. The analogy I use, car crashes out in the country, one car on another car out in the country are much slimmer than if you're driving down one of the interstates in Kansas City. A lot more cars means chances of more collisions. So, what does that depend upon? Well, the concentration of the particles. This is the car analogy. More cars on the road, more chances there are. So the more concentrated the particles are, the more likely a collision will occur. Availability. This deals mostly with the state. If something collides, it has to collide on the surface. So availability is on a surface. So these particles on the surface can be collided with, but the particles underneath are insulated by other particles of the same sort. So to make the availability more, you can grind it up or stir it up. If it's settled down at the bottom, the particles are protected. Particles on the bottom is protected. If it's in one big chunk, particles on the inside are protected. So the smaller the pieces, the more available they are to particles, and usually high temperature. If the temperature is higher, the particles are going to be moving more, and if you're moving more, you're probably going to be bouncing into each other. Think of somebody walking slowly down the hallway in between classes, and if somebody's trying to run down the hallway. The guy running down the hallway, somebody at a high temperature, might bump into more people than if you were moving slowly and walking with care. Another factor is the location on the particle. of the collision on the particle. It's like batting, softball, baseball. There's a sweet spot on the bat where if you hit it, the ball's going to go straighter, longer, farther. So if you hit it right on that sweet spot of the particle, chances are that it will react. Suppose you have a particle that looks like this, and it has to be hit with a particle X. Well, if it hits on the side, nothing happens. The sweet spot would be only those collisions that will hit in between the two, splitting them apart and allowing it to go. If you hit this way, it just moves the particle around. If you hit it this way, you split the particle up, forming a rearrangement of the particles in a chemical reaction occurring. So molecules, things that are covalently bonded, tend to react slower. Ionic compounds, if it's already dissolved, has no partner with it, is an ion, and that means 360 in all directions is available. So any collision with an ionic compound tends to go to completion, which means it has a good enough no location. Location is for molecules, things that are joined together. If it's an ion, they tend to react more often because there's no set location on it. There are exceptions to that rule, of course. And energy of the collision. You have to hit hard enough to break the old bonds and form new bonds. If you just nudge a car, going back to car collisions, you'd have a little bitty bumper, fender bumper thing. Nothing's gonna, your car insurance doesn't get involved. If you hit them, T-bone them from the side, that's going to cause more damage, especially if you're moving faster, and you're going to have more issues. So you got to have enough energy to crack the molecules up to get close enough to the particle to react, if it's an ion, things like that. Due to these three factors, only a tiny fraction of a fraction of a fraction of a fraction of all collisions, a fraction, etc., of all collisions will react. The reason why things react at all is that there are such a humongous number of particles sitting around. So only the tiniest fraction of a fraction of all collisions are successful. That means most reactions are not successful. Another way of looking at this as far as the energy is concerned is an energy diagram. If you get to AP Chemistry, we talk about these more often. Here's your energy level of the reactants. Here's the energy level of the products. And in between there, you have a bump. Sometimes this bump is very tall. Sometimes this bump is very small. This is the activation energy. The activation energy is the energy needed for a reaction to occur. Once you overcome that activation energy, things tend to go. You can think of it like a bonfire won't start until you add a small supply, like a match. A little bit of energy gets it going. Then once it's going, it proceeds on its own. The taller, in general, the taller the activation energy, the bigger the hill is, the slower or more energy you need to put into a reaction. What a catalyst does is it provides a different route. It will kind of tunnel through this activation energy, giving you an alternate route, making less energy so the reaction will go fast. So a catalyst speeds up a reaction. It is not used up. If you have 5 grams of catalyst before, you're going to have 5 grams of catalyst afterwards. It either lowers the activation energy or it improves the orientation. Which enables it to hit the sweet spot better. So if it improves the orientation, it improves the location, chances of a collision on the sweet spot on the collision. So the orientation is another thing that you can do. This is what catalytic converters in your car does. Catalytic converters on your car hold the pollutant, smog producing particles in place and allowing oxygen to hit it, becoming less pollution going on. In biology, they call catalysts enzymes. And it does the same process. So biological catalysts are enzymes. That concludes this lesson on speeding up chemical reactions.